In this video, I want to do a simple one-dimensional kinematics problem. And so it has to deal with the fastest pitch ever recorded. It came off a top speed of 45 meters per second. It was accelerated over about 1.5 meters. And if we assume constant acceleration, what was the acceleration and how long did it take? So let me get pitch. So I'm going to get a diagram here. So there's this ball and it's accelerated over some distance at which it's released. What did my description say? It had a final velocity of 45 meters per second. It was accelerated over a 1.5 meters. And I want to know what is the acceleration and what time did it take to do it. Okay, let me switch over to sort of a schematic diagram here. I need a coordinate system. I'm going to put x along the direction of acceleration. I'm going to say it started at x is equal to 0, and then it was released at a final value of x, which is 1.5 meters, so it was accelerated over this distance. Okay, so if I want to find relationships between my parameters to find a and t, I have a series of kinematic equations that do that. So first, what I need to do is identify two specific points in time, say 2 points in time, sort of t initial and t final. And here's a situation where that's pretty easy. The initial is where it starts accelerating, and the final is where it's released at 45 meters per second. So I'm going to set my origin of time at my t initial, so that's t is equal to 0. My final time, then, I'm just going to call t. It's an unknown. And these are my 2 points in time. So two things have happened here. One of which I've clearly envisioned in my head the 2 points in time I'm dealing with, when it starts accelerating and when it is released. Those are my 2 points in time, and I've also now labeled them. I've decided on an origin of time, set t initial equal to 0, and I've given an expression for my final time, which I've just called t. By the same token, I've established a coordinate system where my initial position is 0, etc. And so usually in kinematics problems, at this point in sort of my brainstorming session, I've got my pictures, I've got a good visualization of what's going on. I like to put down a list of everything I know and everything I don't know. And so, again, it's all related around my 2 points in time and my position, velocity, acceleration, and time for those 2 points in time. So my initial position is, as I've defined it, given my coordinate system, 0. My final position is known, that's given in the problem, that's 1.5 meters. My initial velocity is known, it starts from rest, that's 0 meters per second. And my final velocity is also known, it's 45 meters per second. The acceleration is unknown, that's what I want to know, but I'm assuming it's constant. And so there is no initial acceleration and final acceleration. It's the same throughout. So there's just a, and then there's some initial time, which I've defined to be 0. I get to define my time, 0 of my time axis, and my final time I just called t. Okay, so I want to find a and t here, and I know these expressions. And so as part of the brainstorming point of view, I have kinematics equations that relate all of these expressions together, and I can play with some. I'll give you sort of one clue. If I'm looking for a, say, if I'm not given time, and in this case I'm not, and I'm not trying to find time, which when I'm finding a I'm not, the place I like to start is the expression that relates the final velocity squared to the initial velocity squared plus twice the acceleration times the displacement. And there's just no, I mean, this isn't some sort of law, but it's just a rule of thumb for me. If I'm not given time and I'm not looking for it, I start with this expression because it does not have time in it. And so what does this have? I know v sub f, I know v sub I, and I know the displacement. I know delta x, which is x sub f minus x sub I. So I can use this equation to solve for a. So I'm going to go ahead and go to the solve section and do that. This is 0, and so the acceleration then is v sub the final velocity squared over twice the displacement, which is the final position minus the initial position. And so this is 45 squared over 2 times 1.5. I can put that in my calculator, and I get 675 meters per second squared. I might take a moment out in awe in that a little bit. That's almost 70 g, 70 times the acceleration due to gravity. So that's pretty substantial acceleration. All right, so that's I sort of went to a solve step there. Maybe check a little bit, sort of see, does that seem reasonable? Man, that seems excessive to me, but I might go through in a pretty simple derivation. I can convince myself it's right. The next step then is to go back and look at some relationships that might be able to solve for time. Well, there's the position relationship. The final position is equal to the initial position plus the initial velocity times time, plus 1/2 times the acceleration times the time squared. It's not the time, of course. I just want to be a little careful here. It's the time difference, delta t, times the time difference squared. The time difference in this case, which is t minus 0, once I substitute in t sub final time minus the initial time, is just equal to what I'm calling the unknown t, but I sort of skipped a whole lot of steps there. They may not want to. The thing is, though, this isn't quadratic in t, so I might in fact go with the simplified the linear equation instead of the quadratic one. The final velocity is equal to the initial velocity plus the acceleration times the time difference. Now that I know the acceleration, I know final and initial velocity, I can do this as well. Delta t, which is equal to t, then is equal to the final velocity, I'm losing my pen here, divided by the acceleration, which is 45 divided by 675, and that is equal to 1/15 seconds. And so here's a sort of a straightforward example to use kinematics, but you can see the theme here that's going to be very important in doing these problems. Start with a good picture as well as the all-important schematic. Set your zeros and positive direction of your coordinate system. Set your zero of time. Identify very specifically what you know and what you don't know, and then go to your known relationships that relate these parameters together, sort of brainstorming to see what would be the simplest way to solve for what you don't know with what you know.